Today we are discussing about thermal radiation. So we will give some introduction to the thermal radiation. After conduction and convection, the other distinct mode of heat transfer is radiation. Thermal radiation is electromagnetic radiation emitted by a body by virtue of its temperature. This radiation is widely applicable in industries, and it is having or it is related to our climate change and many other things. In boilers, when the temperature is 1500 degrees centigrade or maybe more, or at higher temperatures, this radiation and its applications are very wide. Maybe in solar thermal power plants or many other cases, we will be using this thermal radiation concepts. Maybe in space applications. In all cases, radiation is playing a very significant role. Now we will see how the development of radiation happened. In radiation, there are two models. One is wave model, and another one is a quantum model. This wave model is proposed by James Clerk Maxwell in 1864. Maxwell is famous for his electromagnetic wave theory and all. Here we can say that wavelength, that is equal to c by mu. What is this c? C is velocity of light in the medium. We all know that C naught, the value is 3 into 10 to the power of 8 meter per second. That is the velocity of light in vacuum. Now coming to the quantum model. This quantum model is proposed by Max Planck in 1900s. And this energy, that's equal to h into nu, where h we can call it as the Planck's constant. Its value is 6.62 into 10 to the power of minus 34 joule second. Here again, maybe we can rewrite it as E is equal to h into nu is c by lambda. Here the energy emitted by the surface, the important thing to note is this energy is inversely proportional to the wavelength lambda. That means when the wavelength is more, then energy is very less. Then what is this wavelength? Wavelength, the unit usually representing is micrometer, or we are calling it as microns. So 1 micron is nothing but 10 raised to minus 6 meter. We discussed, or we had some, it told you regarding electromagnetic spectrum of electromagnetic radiation. So spectrum of electromagnetic radiation, this is the spectrum. We can see that in the axis you can have wavelength, that's in microns. Thermal radiation is mainly from 0.1 to 100 micrometers. When we are calling it as thermal radiation, its value is 0.1 to 100 micrometers. So that region is coming under the category of thermal radiation. And from 0.4 to 0.7 micrometers, 0.4 to 0.7 micrometers, that comes in the region known as visible region. So what all we can see, suppose we are taking a lamp, so we can see the light, because majority of the light which falls under this 0.4 to 0.7 region. So that is the visible region. You can see that I already told you that when the wavelength is small, then energy will be high. So physicists, they may be working in this area, this is X-rays, gamma rays. So here you can see this is ultraviolet, and to the right of this you can see that IR represents infrared. Then from 100 microns onwards is microwave, then radio waves, and on it is going like that. That means people working in the electronics or other scientists, they will be working in this area because the particle energy is very low. Here the particle energy will be emission, that energy will be very high. That's why it has to go for X-rays, gamma rays and all. And the important thing to note is that our study is focused on 0.1 to 100 microns, and in that from 0.4 to 0.7 microns, that is the visible region. So this is all about the spectrum of electromagnetic radiation. You can study this and you should understand how this spectrum works. We have gamma rays this side, we have radio waves and other things that side. That you can refer any textbook or anywhere. So we can have this spectrum of electromagnetic radiation. Now we can see some basic concepts of thermal radiation. The first idea is that solid and liquid surfaces at all temperatures emit thermal radiation. We studied in conduction heat transfer, that is heat flux Q is directly proportional to change in temperature. Maybe we can, this is the heat flux, that it is in watt per meter square. So this heat flux is directly proportional to change in temperature, that is delta T. So this the fundamental law is Fourier law of heat conduction. And if we take the case of convection, this is Q conduction, and if we take the case of Q convection, then the heat flux, that's again in watt per meter square, that's also we can write it as it is proportional to delta T, except for natural convection. That's a special case, and we have to exempt from that, except for natural convection. But in the case of radiation, for Q heat transfer for radiation, it is going to the, so we can write it as T raised to 4 minus the surrounding temperature raised to 4. It is proportional to the fourth power of absolute temperature. Here you have to specially note this temperature, you have to always take in Kelvin. This is a common mistake usually people are doing, because the variation when it's a power coming to T raised to 4, that is in Kelvin and degree centigrade, that variation is very high. And another thing is that we can see that the non-linearity, because when the temperature to the power, then this non-linearity increases in this case. Okay, so the thing is that in conduction it is proportional to change in temperature. In convection also this is proportional to, except for natural convection, the heat flux, that is proportional to change in temperature. But radiation, the important point to note is that for radiation the variation in absolute temperature, that is absolute temperature to the power of 4. When we are considering delta T in both cases, if you are taking the units in Kelvin as well as or in degree centigrade, we are taking this difference. So that will be the same. But here the important point to note is that temperature we have to take in absolute Kelvin. So that is the first point. Solid and liquid surfaces at all temperatures, so they are emitting thermal radiation. Gas is in between the surface. If gas is there, then that also will have some radiation, but for the purpose of this course, we are not taking into consideration of the gas radiation. Another important aspect of radiation is it requires no medium for propagation. Unlike conduction and convection, without a medium also radiation heat transfer can take place, and the best radiation heat transfer is happening in vacuum, because in atmosphere lot of attenuation and scattering and other things are happening. The sun's energy which is coming to the earth, that we can say as an example for this thermal radiation. The important point is that unlike conduction and convection, in thermal radiation it doesn't require a medium for transfer of this radiative heat. Consider a thermos flask. So in the thermos flask, one section I have taken. So here this portion we can consider at a higher temperature, this is at a lower temperature. Then in between is evacuated, that means it is vacuum or it is evacuated, it is vacuum. What is the advantage now? Because there is no contact between this warm surface and this cold surface, conduction is arrested. There is no flow because it is vacuum and there is no bulk movement, so convection is also getting arrested. But in the absence of conduction, also in the absence of convection, there will be heat transfer happening here, and this heat transfer is by thermal radiation. So no medium is required for the propagation of radiation. That is another aspect. Then in conduction and convection, there is no dependence on wavelength, but here this radiation depends on the wavelength. That wavelength maybe that can vary from 0 to infinity. So this thermal radiation which depends on the wavelength. First, it is whatever be the surface in solid and liquid, it is absorbing. Then the second point is that no medium is required for the radiation to travel, radiation to transfer. Then another thing is that the dependence, there is some dependence on wavelength. That wavelength can vary from 0 to infinity. Now we have to define a concept called one more thing is that in addition to emitting radiation surface it is having a capacity to absorb the radiation also. The surface can emit as well as it can absorb. It can absorb all radiation or part. It can absorb all or part of the radiation. Suppose we are considering a surface. We are considering a surface here. Then these are some surrounding surfaces. When we are considering these surrounding surfaces, there is a chance that it can radiate. Here also there is a chance that it can radiate, but there may be some all or part. This surface, in addition to emitting radiation, the surface is having capacity to absorb the radiation. So this surface, which is kept at a particular temperature, having the capacity to absorb all or part of the radiation which is coming from the adjacent surfaces. So that is another characteristic or basics of thermal radiation. Then very important thing is the directional nature of the radiation. You can see this figure. So this is the surface, then from this surface some emission radiation is happening. We can see that a surface emits radiation in all directions encompassed by a hemisphere. So if you are taking the hemisphere, so it can emit radiation in all directions encompassed by the hemisphere. So this dependence on wavelength and this direction, all these things are new when we compare with the conduction and convection types of heat transfer. Next, we have to study a very important concept, an idealization, that is known as black body. What is black body radiation? Black body is one that allows all incidental radiation and internally absorbs all of it. Whatever be the wavelength and whatever be the direction, it absorbs all the radiation incident on it. So this is, there is no perfectly black body available, but this is an idealization, because it will be, by the concept of this black surface or black body, we will be in a position to compare the real surface and other things. So this is somewhat an ideal case. Then what it means? The implication of this statement, implication. That is, there is no reflection, that is zero reflection. Then what about transmission? Because it internally absorbs all of it, that means zero transmittance. And it is true for all wavelength, as well as it is true for all wavelength as well as direction. So it is true, that is zero reflection and zero transmittance, that is whatever be the direction and whatever be the wavelength, it will absorb, a black surface or black body will absorb all the incident radiation. Similarly, black body is a perfect emitter also. At a particular wavelength and direction, it will emit the radiation maximum. Or in other words, we can say that there is no body that can have an emitting capacity more than a black body. So the real surface at a particular wavelength and direction, it is not having its radiative heat transfer capacity will be in the real surface, it will be less than the radiation capacity or the emission capacity of a black body. What are some examples of a black body? That is, there is something called lamp black. So lamp black is an example for black body. One, that is lamp black. Another example is gold black, platinum black, and there are some paints, special paints, which is also having the capacity which is, we can idealize it as almost near to black body, though there is no perfect black body is available. But this lamp black and platinum black, gold black, all that we can idealize it as a black surface. So this black body or black surface is an idealization to compare the performance of the real surface or real systems. Okay. Now comes Stefan-Boltzmann law of thermal radiation. This emissive power of a black body at a particular temperature, that is proportional to the fourth power. In the starting itself we had some idea, it's proportional to the fourth power of absolute temperature. Here this temperature is in Kelvin. Again I am telling, so never put temperature in degree centigrade. Temperature we have to put in Kelvin. Then this MC power of black body, that is equal to a proportionality constant sigma into T raised to 4. What is this sigma? Sigma is known as Stefan-Boltzmann constant. Its value we can remember very easily, that is 5.67 into 10 raised to minus 8 watt per meter square Kelvin raised to 4. But watt per meter square Kelvin raised to 4. That is 5678. 5.67 into 10 raised to minus 8 watt per meter square Kelvin raised to 4. That is the value of Stefan-Boltzmann constant. It will give the MC power of a black body. The Stefan was a Slovenian physicist, and Boltzmann is an Austrian physicist. And Stefan is the research guide of Boltzmann. So this is the formulation of Stefan-Boltzmann law. So that is the basic law. In conduction we have Fourier law of heat conduction. In convection, Newton's law of cooling, and radiative heat transfer, we can have the Stefan-Boltzmann law of thermal radiation. Now another term, that is total hemispherical emissivity power. What is this meaning of total? I already told you that thermal radiation depends on wavelength as well as direction. So this total means, maybe we can write it as its summation of all wavelengths. And what is hemispherical? So hemispherical means we can write it as a summation of all direction. All directions. So this term is very important. The total hemispherical. Total means it's encompasses of all the wavelengths, and hemispherical means it's coming all the directions. Then what is this total hemispherical emissivity power? So we can represent this total hemispherical emissivity power of a real surface. So this is an example for a real surface. So here there is a real surface. In that you can see that radiation is emitting. So it's a real surface, and this is real surface. Okay. And the surface is at a temperature of T star. So this is the radiation flux emitted from the surface of the real surface. Now the same thing I can suppose this is a black surface. If this, I can draw another picture, and if it is a black surface also at the same temperature T star, then there will be this radiation happening. So this is, so the difference is that this is the total hemispherical emissivity power of a real surface, and this is a black surface. Then the radiant, so EB is, that is for the same thing, radiant flux emitted from a black surface. Radiant flux emitted from a black surface. So there is a term called total hemispherical emissivity power. This total means it consists of all the wavelength, and hemispherical means it encompasses all the directions. So that is the case for a real surface and a black surface. So for the real surface, this radiation flux is written as E, and for black surface it is written with the suffix B, EB. Then what is total hemispherical emissivity? Total hemispherical emissivity, that is the emissivity for all the wavelengths as well as for all the direction. This total hemispherical emissivity, I can write it as, it's a ratio of E by that is total hemispherical emissive power of the real surface divided by emissive power of a black surface at the same temperature. At the same temperature. Temperature remains same. So at the same temperature, so total hemispherical emissive power divided by emissive power of a black surface. At the same temperature, I can call it as the term emissivity. So this emissive power of black surface is maximum. That means this value of emissivity lies between 0 and 1. Emissivity, there cannot be more emissivity, the value cannot be more than 1. So I think already we have done some experiment to find out the emissivity of a surface in our heat transfer lab. So this is total hemispherical emissive power. Total means all wavelengths and hemispherical means all directions. This is for a emissive power of real surface. Then we have black surface. So real surface emissive power divided by black surface emissive power, that term is emissivity, also at the same temperature. Then the value of emissivity, it can lie between 0 and 1. We already studied total hemispherical emissive power and total hemispherical emissivity. Now we have to study monochromatic hemispherical emissive power. This monochromatic hemispherical emissive power, we can also say that it is spectral. Another term we can use for this monochromatic is spectral, or we can say that this monochromatic means at a particular wavelength, at a particular wavelength. That means this monochromatic means spectral, or it is at a particular wavelength. Total means it is encompassing all the wavelengths from 0 to infinity. Then we will see what is this monochromatic hemispherical emissive power. That is E lambda. E lambda is nothing but it is a radiative heat flux emitted. So that is small dE by unit wavelength. That means d lambda. So the unit, that is the radiative heat flux emitted. So the heat flux is watt per meter square divided by d lambda. Unit is micrometers. We already the unit of wavelength is micrometers. Then here this is the unit. Then I can write it as dE is nothing but E lambda d lambda. From here, how I can find out this total hemispherical emissive power? This is nothing but if I can integrate it. That is, if I can integrate it from 0 to infinity, then it will come automatically as E. Then this is nothing but 0 to infinity E lambda d lambda. So that means when this E lambda, that is spectral monochromatic or spectral hemispherical emissive power, when it is integrated over all the wavelengths, we will get total hemispherical emissive power. Okay. So now we have this term E lambda. This idea I can explain some more in another way. If I am taking this graph, so this is E lambda, that is in the spectral hemispherical emissive power, and this is the wavelength. Suppose I am taking at a here I am considering this is lambda and this is d lambda. So this because this is lambda plus d lambda, then I can write it as this is d lambda. Then obviously this will be dE, area under this curve, that will represent dE. So this is the radiative for a this is the distribution for a real surface. Okay, then what is spectral hemispherical emissivity power? It is nothing but dE by, that is, we can get this dE, that is equal to spectral hemispherical emissivity power into d lambda. The same thing we can write it here. So from that I can write it as dE is nothing but, we can write it as dE is E lambda d lambda, when this E lambda is a quantity which is when integrated over all wavelengths. When if I am integrating it for all the wavelengths from 0 to infinity, that means from 0 to infinity I will get this total hemispherical emissivity power. So I think the idea is clear. That is, then spectral hemispherical emissivity when integrated over all the wavelengths, when it is integrated over all the wavelengths means 0 to infinity, we will get total hemispherical emissivity power. Then what is so this is monochromatic hemispherical emissivity power of a real surface, E lambda. What is EB lambda? EB lambda is the same thing, monochromatic hemispherical emissive power of a black surface or a black body. EB lambda is the same thing, monochromatic or spectral hemispherical emissive power of a black surface. That is known as that is we are denoting by the term EB lambda, that is spectral hemispherical emissive power of a black surface. Then similar to the previous case, what will be the quantity? And here also we have to note down that this is at a, we are taking at a particular temperature. In what is another next quantity? That is monochromatic hemispherical emissivity. What is this monochromatic hemispherical emissivity? We already studied total hemispherical emissivity, that is for all wavelength as well as for all direction. So this is at a particular wavelength but all direction. Then this is spectral monochromatic or spectral hemispherical emissivity, that is E lambda, that is monochromatic hemispherical emissive power divided by of the real surface divided by that of a black surface. The point to be noted is that these are happening at the same temperature and wavelength. These are happening at the same temperature and wavelength. Then if I draw a spectrum of this is a so in the y-axis this is spectral emissivity power of a real surface, here it is black surface, this is the wavelength. Then this is the case of a black surface and this is the case of a actual surface. If I take a particular wavelength, that I am denoting it as lambda star, and also at a particular temperature, then if I write this is A, this is B, and this one is C, then what is this AB by AC? It is nothing but spectral or monochromatic hemispherical emissivity. It is nothing but this AB by AC. AB by AC. The point is it should happen at the same temperature and also at the constant temperature and at the same wavelength. Same wavelength, the lambda star we are taking as the wavelength. When we are considering that this AB by AC, that is spectral hemispherical MC power divided by of the real surface divided by that of a black surface, we will get monochromatic hemispherical emissivity. Now we have to see that we learned 4 important terms. One is total hemispherical MC power, that we denoted by E. Then total hemispherical emissivity, that we denoted as epsilon. The next term we studied is monochromatic hemispherical MC power, that is E lambda, and spectral or monochromatic hemispherical emissivity, that is epsilon lambda. This total hemispherical MC power is commonly we referred it as MC power. Always we are not saying that it is total, it is not hemisphere. Simply if we say that it is MC power, it means total hemispherical, that is it is encompassing all the direction, that is hemispherical, as well as all wavelengths, 0 to infinity all wavelength it is taking. Simply MC power means it is total hemispherical MC power. Simply emissivity means it is total hemispherical emissivity. Now, always no need to take or no need to tell that it is spectral hemispherical MC power. Spectral MC power itself denotes it is MC power at a particular wavelength. No need to say that it's a hemispherical, it's automatically taken into account. It is independent of the direction, it is applicable to all the direction. In the similar way, spectral or monochromatic hemispherical emissivity, in that case also it is, we can say that it as monochromatic or spectral emissivity. No need to point out again that it is hemispherical emissivity, because when we are saying that it's monochromatic emissivity, it's automatically we can consider that we are referring to a case of monochromatic spectral at a particular wavelength, that emissivity which is happening at a particular wavelength and temperature. So these 4 terms you should have some idea, and that will be required when simply we are saying the term MC power and other terms monochromatic, then immediately we should get the idea, okay, monochromatic, so it is depends on wavelength. Simply emissivity, so that means there is no point in worrying about the wavelength as well as direction. What is a gray surface? You may be coming across the term the surface. In the radiation, the surface is gray diffuse. Then what does this? We already seen what is a real surface, what is a black surface, and now what is a gray surface. You can see that a surface is having the same value of epsilon lambda at all wavelengths. At all wavelengths, if the epsilon lambda is the same, at all wavelengths, epsilon lambda is the same, then we can say that it's a gray surface. You can see from this graph, this x-axis is from 0 to lambda, and this is epsilon lambda. For a black body, so emissivity is varies from 0 to 1, and for a black surface, emissivity is 1, and for a real surface, so this is the variation of, so for a real surface, the emissivity, the spectral MC power, that varies with respect to lambda, but for a gray surface, this is constant, epsilon. So the value of epsilon is constant for a gray surface. Always we encountered a surface like, what is the meaning of this gray and diffuse surface? So gray and diffuse surface. This gray surface means it is independent of the wavelength, and diffuse means it is independent of the direction. So if you are considering the MC power, so we no need to consider it's a total hemispherical, because it is no longer depends on wavelength, it's no longer depend on the direction. So gray diffuse is an idealization, or it's in order to make the problem easier. Usually in the radiation, the term gray diffuse in the problems and all, first they will state the surface you can consider as a gray diffuse surface. Gray diffuse surface means no need to worry about the variation in wavelength as well as the variation in the direction. So that's the meaning of gray diffuse. So once again, this gray surface is a surface having the same value of epsilon lambda. That means along the wavelength, this epsilon emissivity is the same. Now we can move to the laws of thermal radiation. By emissivity power of a black surface is given by Stefan-Boltzmann law. That's nothing but emissivity power of a black surface is sigma T raised T to the power of 4, where T is in Kelvin. So that is Stefan-Boltzmann law. We will get the emissivity power of a black surface. But how to find out spectral black body emissivity power? That is emissivity power at a particular wavelength. How to find out? In order to find out that, we have to go for the Planck's distribution or Planck's law. What Planck's law says? Emissivity power of a black surface at a particular, that is spectral black body emissivity power, that is emissivity power of a black surface at a particular wavelength. That is nothing but that's equal to C1 is a constant. We will see what is C1 and C2. C1 divided by lambda raised to 5 e to the power of C2 by lambda T, the whole, then minus 1. So its unit is watt per meter square micrometer. Unit is emissivity power, already we know that watt per meter square micrometer, that is per spectral per unit wavelength, because in this case it's watt per meter square, but this is for a unit wavelength. So that's why it's coming as micrometers, watt per meter square micrometer. Again, this is for a black body emissivity power, that is Stefan-Boltzmann law, but spectral black body emissivity power is given by Planck's law. Spectral black body emissivity power is given by Planck's law. In the Planck's distribution, in the coming classes we will see the Planck's distribution, and when we are changing the values of lambda, then the spectrum, based on the temperature, this spectrum will be changing, then that will goes to Wien's displacement law and all, that we will see in the coming classes. So then what is the value of C1? C1 is nothing but 2 pi h then C0 square. So C0 you already know, h is Planck's constant. Then C2 is h C0. C0 is the velocity of light in vacuum, and K is nothing but it's a Boltzmann constant, that is 1.38065 into 10 to the power of minus 23 joule per Kelvin. Then this C2, the value is 1.439 into 10 to the power of 4 micrometer Kelvin. Where this T, always we are using T, that is absolute temperature of the surface. T is absolute temperature, lambda is the wavelength of radiation emitted, and K the value is Stefan-Boltzmann constant. So through these classes, what we have learned is we got an introduction to thermal radiation. In the thermal radiation, there are two theories. That is, one is wave model, and another is quantum model. Then from that we come across the electromagnetic spectrum. So in the electromagnetic spectrum, we learn that thermal radiation is from 0.1 to 100 microns. The wavelength we are saying in terms of micrometer or microns, that is 10 raised to minus 6 meter. So this thermal radiation, the visible region is from 0.4 to 0.7 micrometers. Then after that we have seen the peculiarities of surfaces in consideration with radiation. A significant departure from conduction and convection is that here even in vacuum radiation will happen. And another thing is that in radiative heat transfer, the direction is important, as well as this radiation is depend on wavelength also. So depends on wavelength and direction, there can be changes in the thermal radiation. but there is no dependence regarding direction and wavelength in conduction and convection heat transfer. And in vacuum also, this radiative, so it doesn't require a medium to propagate. And there is, we can, all the radiative surfaces, it can absorb radiation as well as it can emit thermal radiation. It can absorb radiation energy from the nearby surfaces, all or part. Then it can emit also. That is the nature of radiative surfaces. Then what is known as, there is an ideal concept called black body radiation. In that black body, in order to compare the real surfaces, we are learning the concept of black body. In the black body, whatever be the wavelength and temperature, what all rays incident on it, it will absorb. So that is how we define this black body. And no other body is, and it's a perfect absorber as well as a perfect black body is a perfect absorber as well as a perfect emitter of heat. No other body is capable of emitting more than a black body at a given temperature and wavelength. So the term at a given temperature and wavelength is very, very critical, because then the terms we had studied is spectral, is total hemispherical emissive power. In the total hemispherical, the word means it encompasses all the wavelengths, and hemispherical means all the directions. Total hemispherical emissive power, that we represented it as E, capital E, then emissive power, total hemispherical emissive power of a black surface. Then the emissivity. Emissivity is nothing but emissive power of the surface divided by emissive power of a black surface. In the similar terms, we have learned spectral hemispherical emissive power of a surface and also spectral hemispherical emissive power of a black surface. When we divide the spectral emissive power of a surface divided by spectral emissive power of a black surface, we will get spectral emissivity. Then we have studied what is all these things. We have studied what is known as a gray surface. In the gray surface, that a surface having the same value of epsilon lambda in all wavelengths. That is, and when we are saying that a surface is gray diffuse, oftentimes this reference is coming in radiation heat transfer. Gray diffuse means, gray means it is independent of wavelength, and diffuse means it's independent of direction. Then coming to, then we have learned this laws of black body radiation. We have Planck's law, we have Wien's displacement law, and other laws. From Stefan-Boltzmann law, there is an equation for black body emissive power. Then spectral black body emissive power is given by this Planck's law, and you can see that EB lambda. So this is the thing. So in the coming classes, we will see Wien's displacement law, then how the thermal radiation is progressing with the other related laws, then radiation exchange between bodies, all that. Thank you.